leading up to our current understanding of the model of our solar system, we start off with about 2,500 years ago, Aristotle, Ptolemy, who was about a couple thousand years ago, 1,900 years ago. One word that I'm looking for right now to describe what these guys said. What's that word? Yep, geocentric. The Earth is the center of the universe. Everything else, including the sun, revolves around the Earth. Geocentric. Fast forward a couple thousand years to Copernicus. What's the one word I'm looking for Copernicus? Yep, heliocentric. Helio means sun, so sun-centered theory. The sun-centered theory of our solar system. All the planets, including the Earth, revolve around the sun. Controversial at the time, widely accepted, universally accepted now. Fast forward about 50 years. Tycho Brahe. He had an assistant named Johann Kepler. And Johann Kepler is the guy we focus on a lot more because he did more than Tycho Brahe did. At least he did more analysis than Tycho Brahe. What did Tycho Brahe do, though? Besides die of a bladder infection at a dinner party because he was embarrassed to go pee. What did he do? Besides get his nose cut off in a duel over a stupid math problem. What else did he do? He collected data. Right? He making naked eye observations of the heavenly bodies, the planets, the stars. He measured distances, measured times, measured angles, and so on. That was his assistant, Johann Kepler, who took that data and put it into 3 laws that describe the motion of the planets, how the planets revolve around the sun. Not why they do. That came later on. We talked about that yesterday. Newton said this is why they revolve around the sun. But Johann Kepler said this is how they revolve around the sun. He came up with 3 laws. The first law we call the law of elliptical orbits. Basically, what did it say? Who's got an answer for me on that one? The law of elliptical orbits. Stephanie? All right. So the sun is somewhere in the universe. The sun is there. The Earth revolves around that sun in an elliptical orbit. Now, the diagram that I drew on the board was a much elongated ellipse. It's not that pronounced in real life, but it's still an ellipse. The Earth revolves around the sun in an elliptical orbit. Now, the sun, wherever it is, determines where the Earth revolves around it. But the sun will be at one of the focal points. So the focal point of the ellipse, in a sense, is what determines where the ellipse goes. The position of the sun determines where the ellipse is going to be. Right, Alana? Right? The second law, called the law of equal areas. This one's a bit tougher to describe in words. Okay, picture the diagram when you're trying to repeat this one. You get the sun. Okay, it's in, let's say, position 1. You get the Earth over here. The Earth and the sun are joined by an imaginary line. That line will sweep out a certain area right here in a certain time interval. So if this time interval is, let's say, 2 months, then the area will be whatever. Zoom forward 6 months, there's still a line, an imaginary line joining the Earth to the sun. If we fast forward another 2 months, then the area swept out by that line, the area that's kind of colored in there, will be the same area as the first area was. So in other words, if T1 equals T2, if those 2 time intervals are even, then those 2 areas will be even as well, or will be equal as well. The law of equal areas. Now, the big implication of that isn't so much about the area. Okay, that's the science behind it. But the implication behind it is that the Earth changes speed. As it gets closer to the sun, it speeds up. And as it gets further away, it slows down. Speeds up, slows down. The speed of the Earth isn't constant. It's not nearly as pronounced as we have it drawn here because the ellipse isn't nearly as pronounced. But it's not constant. It changes speed. The faster you, or the closer you are to the sun, the faster it's going to go. It's almost like, the Earth is going over here. Oh boy, it's getting hot. I better speed up. Okay, that's not why it speeds up, obviously, but it's almost like that. Okay. And finally, the law of periods. The sun has a certain Kepler's constant, and we can find it by dividing t squared by r cubed for the Earth. Or we can find it by dividing t squared over r cubed for Jupiter. Or we can find it by dividing t squared over r cubed for Neptune, or for Saturn, or for whatever planet. Kepler's constant for the sun is equal to t squared over r cubed for whatever planet revolves around the sun. Kepler's constant for the Earth, let's say, would be equal to t squared over r cubed for the space station going around the Earth, or t squared over r cubed for a communications satellite going around the Earth, or t squared over r cubed for anything else that's orbiting around the Earth. So Kepler's constant for one object being revolved around can be found by using data for whatever's doing the revolving. The Earth, Jupiter, Neptune, Saturn, whatever. Kepler's constant for the Earth would be found by dividing or by using data for anything that revolves around the Earth, right? This all explains how the Earth revolves around the sun, but it doesn't explain why. Yesterday we talked about why. Yesterday we said, in a silly little demonstration, we discovered that any two objects with mass exert a force of gravity upon each other. Okay, the old story about Newton sitting underneath the tree, the apple falls down, hits him in the head, bonks him in the head, and he has this epiphany. There's gravity. There's mass of the apple. There's mass of the Earth. That's why the apple is attracted to the Earth. That's why I'm attracted to the Earth. That's why I don't rise up and fly off into space. That's why the Earth revolves around the sun and the moon revolves around the Earth. Because for every two objects with mass, there is a force of gravity that's exerted between them. Now, that force of gravity between the Earth and the sun is really, really big. It's got to be. If you want to keep something as heavy as the Earth in orbit, you've got to apply one heck of a force on the Earth. Why is the force of gravity between you two, between two people in front of the room here, not very big? Yeah. Because you don't weigh very much. Okay, relatively speaking, compared to the Earth, compared to the sun, you guys are essentially weightless. Right? You guys have no mass compared to the Earth and compared to the sun. So how do we find the value of this force of gravity? How do we find an actual number that represents this force of gravity? The small force of gravity that acts between these two guys in the front of the room, or the big force of gravity that acts between the Earth and the sun? Well, Newton derived an equation for it. There's that absolute value sign again that's rearing its ugly head for the second time this year. First time it appeared was with friction. What did it mean? Why did we put the absolute value sign in there, Lewis? Yeah, so basically what we're saying is that, look, force is a vector. It has a direction. But the equation that I use to find it, if I put absolute value signs around it, isn't going to tell me what the direction is. So just like with friction, you calculated the force of friction, but you only ever calculated the magnitude of friction. You had to figure out what the direction was some other way. Same deal with gravity. You're going to find the magnitude of the force of gravity that exists between two objects, but you're not going to find the direction. You're going to have to figure that out some other way. Now, don't write this down quite yet. We know the force of gravity is m times g, right? M times 9.81. That'll give us the force of gravity between the Earth and the sun, right? No, it won't. Well, it will, actually. It will. The problem is, I don't know what little g is. Little g is 9.81 when I'm on the surface of the Earth. Okay, the force of gravity between me and the Earth is m times 9.81. But the force of gravity between you and you is m times g, but g isn't 9.81. We don't know what it is. The force of gravity between the Earth and the sun is m times g, but we don't know what little g is. So we can't use this equation unless we know what little g is. And right now, all we know for little g is 9.81 on the surface of the Earth. So we've got to have another equation that's a little bit more general, that allows us to find the force of gravity between any two objects, not just between any object and the Earth. That equation is going to go like this. Not little g, big G. Big G. I'll tell you what that is in a second here. Times m1 times m2 over r squared. Big G is a constant. It's just a number. We call it a universal constant, meaning it's the same number anywhere you go in the universe. Sometimes I call it a fudge factor. F is not equal to m1, m2 over r squared. We got to put a number in front of it to make it equal. A fudge factor, a constant. G is equal to 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. It's kind of an ugly number. The good news is you don't have to memorize that because it's on your data sheet. You want to find the force of gravity between the Earth and the Sun? What's m1 going to be? Mass of the Earth or mass of the Sun? Mass of the Earth, who agrees? Okay, mass of the Sun, who says mass of the Sun? Mass of the Sun? Who says who cares? M1 times, answer this question for me, please. Tyler, what's 1 times 2? Good. Okay, Brian, what's 2 times 1? Good. So it doesn't matter whether we go 1 times 2 or 2 times 1. It's the same answer, right? It doesn't matter whether you go mass of the Sun times mass of the Earth or mass of the Earth times mass of the Sun. Right? Same thing, right? So basically what we're saying here is that M1 and M2, it doesn't matter which one you call which. They're the masses of the two objects. Call whichever one you want, M1. Call whichever one you want, M2. Just make sure that both of the masses are included and make sure they're in kilograms. I'm not going to ask you what R is because it's kind of an invitation to get the wrong answer. I would bet $5 to anybody in this room that if I asked you what R means, the person that raised their hand would say radius. R is radius. Of course it is, right? Well, no, it's not here. Well, I shouldn't say that. It can be, but not necessarily. R is the distance that separates the two objects. In fact, the distance separating the centers of the two objects. And that's going to be measured in meters. So the distance that separates the middle of Jarrett and the middle of Earl. The distance that separates the two of them. The distance that separates the center of the Earth to the center of the Sun. The distance that separates the center of the space station to the center of the Earth. Now, that could be a radius. We're talking about the Earth going around the Sun. The distance that separates the two is the radius. But when we're talking about these two guys at the front of the room, Jared and Earl, then that's not a radius because nobody's going in a circle. It's just a distance. So think of it as the distance that separates them. If it happens to correspond to the radius of a circle, great. If it doesn't, that's okay. Don't think of it that way. Okay, don't think of it as the radius of the circle. What does F stand for? This is the easy one, right? F is the force of gravity. And it's measured in newtons. Now, the force of gravity acting on you, caused by the Earth, is m times little g, m times 9.81. It still is. Could we use this equation to describe that as well? Sure we could. As long as we used your mass, the mass of the Earth, and the distance from the center of you to the center of the Earth. What do you think we'd get for that force of gravity? Same as we get when we multiply m times 9.81. Get the same value. Just two different ways of finding the same thing. When little g is 9.81, it's valid. It works. It's just that it only works when you're on the surface of the Earth. All right? Now, we're going to start off with a problem here, a problem that is a little bit tricky for a first problem. Arguably our trickiest sample problem yet. Not crazy hard, but it's a little bit tricky. Because Mount Logan in the Yukon is 5,959 meters above sea level. Think about that. Calgary is about 1,000 meters-ish above sea level. My son the other day saw the GPS on my windshield, and it has the elevation. He saw that it was about 1,060 meters above sea level. And my 11-year-old son said, Calgary is a kilometer? He knew that that was a kilometer. He said, Calgary is a kilometer up in the air? Yes, Calgary is a kilometer up in the air. That's why the air is thinner in Calgary than it is in other places. That's why Olympic athletes for the 1988 Olympics came to Calgary early to train, because they had to get used to the elevation of Calgary so that they could perform at their peak. Okay. The elevation of Calgary is a kilometer up in the air. The elevation of Mount Logan is almost 6 kilometers up. That's a long ways up. Okay, 6 kilometers doesn't sound like a long distance horizontally, but when you're talking up in the air, that's a long distance. Okay, that's the highest peak in Canada. Now, the Earth's mass is 5.97 times 10 to the 24, and the radius, okay, at the equator, which we'll say is sea level, 6.38 times 10 to the 6. We want to find the weight of a person at the top of the mountain compared to the weight of the person at the base. Well, the weight is the force of gravity, right? Surface of the Earth. We should just say F is equal to m times g for this, right? Because weight is the force of gravity. We're looking for force of gravity. F is equal to m times g. Here's our problem. Here's our problem. When you go up 6 kilometers in the air, little g is no longer 9.81. It's close. It's not like it's like 5.3, but it's not 9.81. It's measurably less than 9.81. So if we don't know that little g is 9.81, we've got to use that general equation that we just learned. Now we want to find the difference in weight. So we're going to find the weight at the top, and we're going to find the weight at the base of the mountain. The weight at the top is gm1 m2 over r squared. So we're going to say that's 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 times the weight of u, or the mass, I should say, of u, which is 55 kilograms. We divide that by r squared. That's 5.97. No, it isn't. It's 6.38 times 10 to the 6. Squared. Do this on your calculator. Follow along with me and do it yourself on your calculator, because this is a little bit ugly, actually. We get that square on the bottom, and we get this big exponent on the bottom that's inside that square, inside those brackets. Okay, do this on your calculator along with me to make sure you can get the right answer, okay? Don't try to do it yourself. Okay, do it with me. Do the steps, follow the keystrokes that I followed. 6.38 times 10 to the 6, and it's squared. See that now? All right. So follow along and do it with me. You got 6.67. Go second function EE. That's my exponent. That's my 10 to the whatever. That's my scientific notation. Don't do this whole 6.67 times 10 to the, don't do it that way. Okay, that's not the way your calculator intended it to be done. 6.67 EE negative 11 times 5.97 times 10 to the 24 times 55 divided by, what should I do next? if in doubt, use a bracket. 6.38 times 10 to the 6. End the bracket, and then square everything inside those brackets. You should end up getting 538.0486. That's your weight, or that's the 55 kilogram guy's weight at the top of Mount Logan. All right, let's find the force of gravity at the base now. This is going to be G m1 m2 over r squared. Now, we should be able to use m times g here, m times 9.81, but since we're dealing with this general form of the equation, let's keep dealing with it. Let's just keep on that trend here and see what we get using that equation. 6.67 times 10 minus 11, 5.97 times 10 to the 24, 55 kilograms. They say masses. It's the weight or the force of gravity that changes. Oh, wait a second. Wait a second. Wait a second. Oh, does anybody see what I've done? Right, what have I done here? Yeah, what have I actually just found? That 538 newtons. Yep. Yeah, this is the base. I didn't include the distance above sea level. Okay? This is from sea level to the center of the Earth. This is the force of gravity at the base. The good news is I had to do that calculation anyways. The bad news is I didn't do it at the right time. All right, so let's say at the peak of Mount Logan now, the distance from the center of the Earth to where I am is not 6.38 times 10 to the 6. 6.38 times 10 to the 6 plus 5959. Think you're going to get a bigger number there or a smaller number? Do you weigh more or less at the top of Mount Logan versus the bottom of Mount Logan? Yep. Yeah, good. It's going to be less because you're dividing by a bigger denominator. Good. So what's a good way to lose weight? Climb a mountain. In a couple of ways, right? A, because gravity is less at the top of the mountain and you will truly weigh less. B, because, well, if you climb 6-kilometer high mountain, odds are you're going to lose weight anyways by climbing that mountain. All right, what do we get for this? Let's calculate this on the calculator as well. Okay, follow along with me to make sure you get the right answer for this one as well. Okay, 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 times 55 divided by, use some brackets. Oh boy, do you ever have to use brackets on this one. 6.38 times 10 to the 6 plus 5959, end that bracket and square it. Remember, you're squaring the entire distance, not just one of them. So let's put in brackets, get a number, and then square it. Press enter. Get 537.0449. What's the difference in your weight? Oh, easy question now. Difference in your weight is 538.0486. Subtract 537.0449. What do we get for that? About a Newton? What's the difference there? 1 point, I don't know, about 1.0 newtons, isn't it? What is it? 1.00? Now, that's not very much, right? The difference in weight between the top of the mountain and the base of the mountain, 1.00 newtons. That's a small, small amount, but it's still a difference. It's a measurable difference. Right? Your mass is the same, but your weight is different. Got it? A little bit of a tricky question in that A, we had to find a difference, so we had to find force of gravity twice. B, we had to add two numbers together to get R. Pay attention, okay? Pay attention to that. Be aware of that when you see a question. Can I just use the number that's given to me, or do I have to add a couple numbers together? Reason through it. Understand why you add two numbers together. Understand why you don't sometimes. And do it. Try these two questions, please. Easier questions, I think, except that in number 2, you actually have to do a little bit of rearranging, okay? Work on that. Let me know if you have any questions, and we'll give you a hand, okay? All right, question number 2, everybody. This one's a little bit of a challenge in that we have to rearrange to solve for one of the masses. Conceptually, it's not hard at all. Okay, rearranging mathematically, a little bit tricky here. It says the mass of the Titanic is 4.6 times 10 to the 7 kilograms. Now, that's not nearly as much as the Earth or the sun, not even remotely close, but it's heavy. Okay, we're still talking about millions of kilograms here. It's a heavy ship. So, because of that, there is going to be a very measurable force of gravity acting between that ship and this iceberg. A measurable force. 61 newtons. That's a big force. That's 10% of my weight. Okay, the force of gravity between the ship and the iceberg. Now, because the ship is so heavy, it's not going to be enough of a force to actually pull the ship towards it. It takes a drunken sailor to pull the ship towards the iceberg. Okay, not the force of gravity. We want to find the mass of this iceberg. So we're going to say that F is equal to G m1 m2 over r squared. What are we solving for here? Yep. M2, M1, doesn't matter. Okay, one of the masses here. We'll call it M2. Now, you guys are going to do this for me. Think back to the beginning of the year when you guys struggled so much with rearranging simple equations like V equals D over T. We went through that little lesson about what you do first. Okay, the first thing that you take away when you're trying to solve for M2 is what is not attached. Is there anything that's not attached here? Is there anything in here that's not attached to the M? The R is attached. It's divided, right? What about the G? Is it attached? Yeah, it's multiplied, right? Everything's attached. So now let's get rid of what is attached. What do you want to get rid of first now? G, M, or R? They're all attached. Doesn't matter what order we do it in. What do you want to get rid of first? All right, so how do we do that? Okay, so multiply it. So it becomes F times R squared equals G times M1 times M2. Good. Now what? What's next? Yeah, Jacob? By the G? Oh, at the same time? Absolutely. Yes, you can. Since they're both multiplied by M2, then yeah, you can take them both over at the same time. You don't have to. You can take G over by dividing, and then you can take M over by dividing. But if you want to take them at the same time, go ahead and do that since it's the same operation. F, a little bit easier that way, right, Jacob? F times R squared over G times M1 equals M2. All right. So the force here, 61 newtons. R, what was R? 100 meters. Divided by G, which is 6.67, times 10 to the minus 11, times M1, 4.6 times 10 to the 7. Okay, again, follow along with me on your calculator. Enter the keystrokes as I enter the keystrokes to make sure that you get this right here, okay? We're going to say 61 times 100. We're going to divide that by, Stephanie, what do you want to do here right now? Brackets. Okay, brackets. Did I make a mistake there? Oh, it's 100 squared. Thank you. Okay, I'm glad you guys caught that now instead of later on. So it's 61 times 100 squared. And then Stephanie said we want to use some brackets here, right? If you go just, watch what happens if I do this. 61 times 100 squared divided by 6.67. If I don't use brackets there, then I'm going to get a number for this, and I'm going to multiply it by 4.6. What my calculator is going to do is multiply the whole thing by 4.6, not the bottom. Okay, I need to use brackets for the bottom only to be multiplied by the 4.6. So bracket 6.67 times 10 to the minus 11 times 4.6 times 10 to the 7, is that? 10 to the 7. End the bracket equals, oh boy, lots of decimal places there. 1.98 times 10 to the something. You can count the decimal places. Watch this though. Watch this little trick. Second function mode. Switch it into, sorry, no, just mode, not second function mode. Switch into scientific notation. Then take that number and multiply it by 1. 1.99 times 10 to the 8. Oh, but wait. How many digits should we be? 2. So it should be 2.0 times 10 to the 8, right? Good? How many people got that? Good. Good. Excellent. Let's try another one now. This is 4.3 on page 209. During a lunar eclipse, Earth, the moon, and the sun are aligned on the same plane as shown in 4.19 here, the diagram that you got at the bottom of the page here. Using the data in the chart below, calculate the net gravitational force exerted by both the moon and the sun on the Earth. So clearly this isn't drawn to scale, but it's the basic setup of a lunar eclipse. You got the Earth right here, and you got the moon over here, and you got the sun over here. You can't see the moon basically because the moon is in the shadow of the sun. The shadow of the Earth, right? So the sun's light doesn't reflect off of it. That's how we see the moon, right? Sun's light reflects off of it. We don't see it here because it's in the shadow. All right, so how do we find the net force exerted by both the moon and the sun on the Earth? Two forces. What do you do whenever you see two forces acting on an object? What do you got to do? F net, but even before that, I'm thinking of a 3-word answer or even a 3-letter answer. Zane? Free body diagram. Good. Free body diagram. The moon pulls the Earth to the left. This is the, let's call it Fm, the force of the moon. Usually what I do is name it the force of one acting on the other. So this would be the force of M acting on E, the force of the moon acting on the Earth. Okay, but when we start saying that out loud, it doesn't sound so good. I'll let you figure out why it doesn't sound so good. Then there's the force of the sun on the Earth. The sun pulls the Earth to the right. That would normally be called FSE. We'll just call it Fs here, the force of the sun acting on the Earth. Now, there is a force of the Earth acting on the moon to the right, but I don't care about that because that's not what I'm trying to find. The sun is also pulled towards the Earth, but I don't care about that because it's not what I'm trying to find. I care about these two forces that act on the Earth. The moon pulls the Earth to the left, the sun pulls the Earth to the right. Now what? This is what I always do when I have two forces, draw a free body diagram. Zane nailed that. Then what? Somebody actually said that. Somebody alluded to it just a minute ago, and I can't remember who it was. Stephanie? F net. F net is equal to the sum of the forces, right? We'll say F net is equal to Fm plus Fs, the force of the moon acting on the Earth plus the force of the sun acting on the Earth. Now, normally at the next point, we'd say m times a, but we're not looking for the acceleration, so let's just leave it as F net. What's the value of Fm? Oh, wait, we don't know. Well, we better find it. We can find that, right? We just went through that process in an example problem and then a couple practice problems. The force of the moon acting on the Earth is g m1 m2 over r squared. 6.67 times 10 to the minus 11 times the mass of the moon, which is, what is the mass of the moon? 7.35 times 10 to the 22. That's the mass of the Earth. 5.97 times 10 to the 24. Divided by The distance from the moon to the Earth, 3.84 times 10 to the 8. Look a bit messy there. Can you guys tell what I'm doing there? Does that make sense? Derek, does it make sense? Okay, let's figure out what that is. 6.67 times 10 to the minus 11 times 7.35 times 10 to the 22 times 5.97 times 10 to the 24. Let's divide it by, use some brackets here, 3.84 times 10 to the 8, and the bracket, square it. There we go. 1.9848 times 10 to the 20. That's a massive force. That's a big, big force. 1.9848 times 10 to the 20 newtons. Why is it so big? You got two big masses. Two massive masses. Okay, the force between you and your partner the other day when we did that silly little demonstration was negligible because your masses were so small. These aren't so small. This is a very big force. So Fm, there we go. Let's find Fs now. Mass of the Earth, we're going to go with 5.97 times 10 to the 24. As the mass of the Sun this time, 1.99 times 10 to the 30. Look at that. It's 1,000,000 times heavier almost. 500,000 times heavier. Something like that than the mass of the Earth. So the Sun's pretty big. It's 1,000,000 times heavier, and it's all made out of gas. It's got to be big, right? The Sun is pretty big. R is 1.5 times 10 to the 11. The good news is it's far away. It's 1,000 times further away from the Earth than the Moon is. Don't forget to square that. Let's calculate this one now. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 times 1.99 times 10 to the 30 divided by, let's use those brackets again, 1.5 times 10 to the 11. Let's end those brackets, square it. What do I get? 3.52 times 10 to the 22, 3.5218. All right. Let's add them up. Add them up. The force of the Moon was 1.9848 times 10 to the 20. The force of the Sun, 3.5219 times 10 to the 22. Is this right? Lewis, where's my mistake? Fm should be negative. That's why I drew my free body diagram, was to recognize what should be negative and what should be positive. Fm is negative. Let's put it in there as such. Add these two numbers up now. We get 3.50 times 10 to the 22. Yeah. There we go. That makes sense. What have we just done? Well, we've combined a problem that we just did earlier today, F is equal to gm1m2 over r squared, along with problems that we did in our last unit. F net is equal to the sum of the forces. It's really no different than those two questions combined, right? This is just yet another one of those F net is equal to the sum of the forces problem. We did the elevator problems. We did the inclined plane problems. We did the pulley problems. Here's a gravity problem. Same thing. We did the vertical circular motion problems. F net is equal to the sum of the forces. Same thing, except that our forces are based on a new equation, gm1m2 over r squared. All right, everyone, I'd like you to try 2 questions on page 209. The first question is exactly what we've just done. The second question, not quite exactly what we've just done. I'd like you to give it a try, though, without my help at first. I'll give you a hand with it if you need it, but I'd like you to give it a try yourself, okay? That's taking it to the next step. Okay, again, number 1, just repeating what we just did. Number 2, you're going to use your brain a little bit more on that one. See what you can do. All right?